Greetings, everyone. All right, today we're going to start off by talking about even and odd functions. So when we're dealing with a function, how do I prove that it's even or odd, whether it be graphically or algebraically? Quick little preview, we'll take more notes here in a bit specifically about this. But if a function is even, it's symmetrical about the y-axis. And if a function is odd, it's symmetrical about the origin. So again, that's our objective today. We want to prove even or odd graphically or algebraically. So let's talk about even functions graphically. An even function has y-axis symmetry. So y-axis symmetry, what that means is for every point x, y on the graph. So for example, if I said this point was 5, 1, then the point negative xy, in this case, if I can prove it, negative 5, 1 is also on the graph. So you can see we talk about that perfect flip over the y-axis, but we can prove it with numerical values as well. All right, now let's talk about odd functions. Odd functions have origin symmetry. So there's two ways you can think about it. You can think about 180-degree rotational symmetry. That's the way I think just because geometry and those visuals connect with me. So if I rotate 180 degrees, I end up with the other half of the graph of the function. But we can also look at it as a double flip, meaning I can flip over the y-axis and flip over the x-axis. So some of you, that might connect better with you. So in that case, what that means is if I flip this way over the y, and then I flip down over the x, I do end up on that graph. Point-wise, numerical or coordinate-wise, what that means is if I'm still at that 0.5, negative 1, take a look. Now I'm at, excuse me, that's positive 1. Oh my goodness. If I'm at 5, 1, I'm at negative 5, negative 1. So you'll notice the values went from positive to both negative. So that's how we can decide using coordinates if they have that odd if it's an odd function because it has that origin symmetry. All right, so let's address x-axis symmetry. We've talked about y-axis, we've talked about origin symmetry, but we also need to address x-axis symmetry. Why is that not an option? And that's because if I look at x-axis symmetry using this visual representation here, we're dealing with functions. I really want to concentrate on functions. So if we think of the rule about a function has to pass. Let's see if you can remember. That black line is a what? It is a vertical line. So we have the vertical line test we have to consider still. So in this case, this is not a function. All right, if it's not a function, we're not going to be working with it right now. So we do not need x-axis symmetry because x-axis symmetry cannot be a function. So if you're asked to prove why for any reason, you can use the fact vertical line test can be your reasoning behind that. All right, so what if I don't have a graph in front of me? What if I don't want to plug it in the calculator and try to figure out coordinates? In this case, you can also solve it algebraically. Algebraically, here's the rule. The rule says a function is even if f of negative x is equal to f of x for every number x in the domain. Sort of wordy, right? So what that means is if you plug in a negative x into the function and you get the original function back again, then it's even. So we're replacing every x value with a negative x, simplifying it, and see where we end up. So we're going to use these two examples on this slide twice, okay? So maybe leave a little bit of space around it. So let's jot this down at any time. If you need to pause, make sure you do that. So in this case, if I plug in negative x for x, use parentheses, that way you're using any signs or exponents correctly. Now I need to use my simplifying rules. Anything to an even power becomes positive. Negative to another even power, so that x remains positive. And that positive 1, of course, that's not going to change because there's no variable there. Now if I compare, every single sign is the same that it originally was. So because of that, we would say, yes, this is even. Okay. Leave about the same amount of space around this or next to it because we're also going to use the same examples for odd. Again, quick visual, if you do plug it into your calculator, I would need to see a sketch of this. So if your proof is that it has y-axis symmetry, how do I know that? You're not going to be able to show me your calculator every time you do a problem. So if that's the case, just draw a quick little sketch to prove that to me, all right? If you're not doing it algebraically, if you're proving graphically, show me the graph. Here, let's try this one. So again, I want to replace x with negative x. Use parentheses. All right. In this case, I have an odd degree. So in that case, or an odd exponent, so my variable is going to remain negative. I'm going to kick it out front because that's typically how we write it, right? And then I've got a double negative, so that would become positive. So now if I compare to the original, every sign is different. So it's not even, but I'm just going to kind of leave that hanging, leave a little bit of space around this because we're going to address the fact there's a pattern there when every sign is the opposite. What does that mean? If you were to look at it graphically, this might give you a hint. We'll come back to this again, but maybe that gives you a hint on what we're going to encounter. All right, so let's take a look at the rule for an odd function. So for an odd function, it is odd if you have f of negative x equals negative f of x for every number x in the domain. So what does that mean? If you plug a negative x into the function and you get the negative of the function, meaning, here's the shortcut, if all terms change signs, then it's odd. Okay, so if every sign changes, every term, that's a key word there too, every single term. So looking back at those examples again, all right, we already looked at this one. When we plugged in a negative, we arrived back at where we were. So you don't really need to rewrite this, okay? So this is still even, and we could tell by the graph. But now let's go back to this one. Look back at your work. You might want to add some information. But here, when we plugged in that negative x, every single sign changed. Every term's sign changed. When that happens, that's when it's an odd function. Okay, and I told you that graph kind of previewed, maybe gave it away because you can see that 180-degree rotation, or you can see that double flip depending on how you think of things. Okay, so if it all stays the same, even. If it all changes signs, odd. If a function's neither odd or even, we just say neither. I mean, you can write out a sentence, it is neither odd or even, or you can just write neither. That's fine with me for our class. Let's take a look at a couple more of examples. So let's determine if they're even, odd, or neither. No matter what, to find out, we have to plug in a negative x for our x value. We're going to substitute that in. In this case, I have a negative to an odd degree, so it's going to remain negative, and that 1 doesn't change. So now if I take a look at my signs, this sign on this term changed, but this one stayed the same. So if you have a mix, it's not all even, it's not all odd, so that's where you would say neither. It's neither odd or even. Take a look at another example. So in this case, make sure you use parentheses so you know how to utilize those exponents. So I have an even degree, an even exponent, so that makes it a positive x. Here I have an even exponent, so that's going to remain a positive x squared. and then I've got a plus 2. So in this case, if I look back, I'm visual, so that's why I'm circling these. Same sign. Oops, I should look at this one, the original. Same sign, same sign, same sign. If it's the same, it's even. Okay, so quick review of what we've got going on here. So we've got 3 options: even, odd, neither. Okay, even means it can be flipped in the y graphically, or all same signs, right? If it's odd, odd means rotated 180 degrees visually, or all signs change. Okay, so I need to see proof. I need to see a graph to prove it. You would draw a graph if you're showing me that way, or you would show me the algebra work if you were going to show me this way. Okay, so keep that in mind on an assessment. I'm going to ask for proof. And then if it's neither, obviously none of those options apply. Okay, so no rules apply, no rules happen. There's a lot of ways you could explain the neither. All right, so let me know any questions you might have, concerns. Keep me updated. Remember, it's very helpful if you have any questions to rewatch the video. Sometimes when you're writing, you're distracted. So going through and just listening once through without writing or any of the distractions can be very helpful. So until next time, have a good day.